Yes, good morning, students. So in the previous class, we have seen some of the topic which are related to intrinsic and extrinsic semiconductors, how a material which is called as silicon is performing in the presence of both intrinsic as well as extrinsic properties, how the holes and electrons are present in the recombination region, why there is a necessity to recombine the holes and electrons with respect to each other. These are all the things that we have seen in the previous class with some solved gate problems. I have told you some of the equations which are related to minority change carriers. We have seen what is the condition if they have given the assumption as all the state as equilibrium, all the state as is in equilibrium state, then you have to give the particular value as 0, and in this case no boundary condition can be established. That's what we have seen in the previous class with some 2 to 3 gate problems, and I have told you to solve for 4th and 5th problem. So I think you might have solved, and some of them has told me the answer also. Yes, it is absolutely correct. 10 power 44 centimeter per second per minus 1 will be coming as the answer, and by keeping the center plot as the electric field, you have to plot the graph. That also you have uploaded. Yes, it is good. And now see, with these basic topics, we are going to study about generation and recombination of carriers that I will discuss in this today's class. And after that, we will also see about the Poisson and continuity equation. In the Poisson and continuity equation, surely 1 or 2 questions will be asked in your gate point of view. Okay, the Poisson and continuity equations are very important. Okay, so now let us see the generation and recombination of carriers. See, we all know that the fundamental unit of electrons and hole pairs in an inorganic semiconductors corresponds to an electron transition between the valence band as well as the conduction band. See, I repeat again, the fundamental unit where the electrons and holes are combining with each other, or we can say it as a recombination state, that is denoted as an inorganic semiconductor that corresponds to an electron transition between the valence band and the conduction band. That's what we have seen in the intrinsic semiconductor case. Whenever recombination of electrons and holes takes place, automatically a transition between valence band and conduction band will be present. Suppose, let us consider the same situation where the electrons and holes are being paired with respect to each other, and in this case the recombination takes place in a reverse transition. Now what you are going to do, that's what we are going to discuss in this particular class with some equations. That's what I have given here. The carrier action is normal. That is called as intrinsic and extrinsic semiconductors. No problem is going to arise. You are just going to combine the electrons and hole pairs. So there you are not going to figure out any problem. But now the reverse condition has been applied here. Since reverse condition has been applied in this case, we have to check what is the carrier action, what is the carrier motion, what is the carrier recombination rate, and how the carriers are generated in reverse action. Okay, so you can see that that's what I have denoted here. What happens now? Your question arises, what happens after we figure out how many electrons and holes are in semiconductor, that too when a reverse action is taking place. Okay, so now let us go to the next slide. So you can see there, first carrier motion. Okay, the first carrier motion, 2 different types of motions are there. One is normal motion and the next one is reverse motion. So first let us discuss about the normal motion case, and it is called as carrier motion 1. In this case, 2 different concepts will be defined. One is by using the conductivity rate sigma, and the other is by using the mobility rate, which is defined by mu. Conductivity is also called as the resistivity. In this case, you can represent the resistivity as rho is equal to 1 by sigma. Therefore, a zero field moment will be captured in this case, where if the electrons are moving from negative side to positive side, a random zero field movement will be generated, and in case of energy distribution across the entire network, a thermal zero field moment will be continued in the network. That represents that the electrons are being scattered by many types of impurities. See, now you have to overcome these impurities. What you are going to do? That is the next case. Okay. Since we are having some defects, we are having some impurities that are present in both N as well as P region, we are going to eliminate the impurities and defects. So what we are going to do means, in this case, we are going to apply an external force. We all know that whenever an external force is applied, the electrons will move in the opposite direction with respect to holes. So automatically a neutral condition is going to occur here. Our main objective is to make both N as well as P junction to be remaining in neutral condition. Okay, that's what they have defined by using the word which is called as random field movement of electrons. You can see here. You can follow my mouse cursor. So you can see there random zero field movement of electrons. That means electrons are moving from negative side to positive side. So in this case, you are going to overcome the impurity by applying the external force. Next. So you can see there, this is the external force which I have applied here. This orange color round box represents that the external force has been applied. And since external force has been applied, many electrons that are scattered by impurities and the defects present in the system will be completely removed. So this is your schematic overview of carrier motion that is present in the first phase. Now let us move to the carrier motion 2, and we will define this by using some equations here. So what I have already told you, we are going to apply some external force here. So you can see there the force can be defined by using the formula F vector is equal to Q into E vector, which is equal to Q into Ex into X bar. Okay. So 1 minute, I think I am stuck here. I will reopen it so that you can see it again. Okay. So 1 minute. Okay. So we are seeing about the carrier motion 2. Okay. So see here. So we are going to apply a force here in order to overcome this particular zero field moment which are present with impurities in this case. So what we are going to do, we are going to apply an external force here. So you can see there the external force is given by the formula F vector is equal to Q into E vector, which is equal to Q into Ex into X cap. Now after applying the force, automatically what is going to happen here, the electrons is going to be getting accelerated with respect to each other. That's why you are getting this equation as minus N naught into Q into Ex. That means at the N side, the electrons are passing from negative to positive side. That's why N naught into Q into Ex will be differentiated with respect to the time period dt. So it is equal to dpx divided by dt. In addition, we all know about the formula for force. F is equal to m into a, which is a derivative of time. So that's why px is replaced by using mv, d of mv divided by dt. Okay. See, in this case, by applying an external force, two different conditions are there. One is the acceleration moment and the other one is the decelerating moment, which is exactly opposite to that of accelerating moment. So in this case, a damping force will be obtained, and as a net result, deceleration of the electron movement is going to take place. So that's why again dpx divided by dt will be defined by using the formula minus px divided by tau. Since it is exactly opposite to that of acceleration moment, we are getting minus px divided by tau. Okay. Now this carrier motion 2, what we have to do means we have to combine both acceleration as well as deceleration moment and we should make the net value equal to 0. That's why in this case this equation is solved. So you can go to the previous equation dpx divided by dt, which is equal minus px divided by tau, which is equal to 0. Okay. So here the net sum provided by the carrier motion 2 is automatically equal to 0. That's why you are getting the formula for mu n as well as mu p in case of mobility as q into tau divided by mn and q into tau divided by mp. See, in your gate question, they will ask you what is the mobility of n type during carrier motion 2 as well as mobility of p type during carrier motion 3. Okay. And types of motion. See, carrier motion 1 and carrier motion 2 are important. Okay, carrier motion 3 is a combination of both carrier motion 1 and carrier motion 2. Okay, so here they have expressed it as a separate carrier motion, but usually two different carrier motions are represented, and this equation is solved only for mobility cases as well as for making the acceleration and deceleration conditions to be equal to 0. Next, we are going to see what is the current density that is passing through a particular area whenever both carriers as well as holes are being regenerated with respect to each other. So you can see there the current density which is represented in this case is always equal to minus q into n naught into Vx. The unit for Jx with respect to a particular area is ampere per meter square, and in this case we can define the current density using the conductivity rate also, and it can be represented by using the formula sigma n into the applied electric field Ex. Okay. So suppose in case both electrons and holes are present in the same region without recombining themselves, then automatically the current density vector will be represented by using E vector divided by rho. We all know that 1 by rho is equal to sigma. So that's why J vector is equal to E vector divided by rho. So this is your exact current and resistance which is provided whenever the electrons and holes are being passed with the externally applied electric field. So you can see there, here itself you can able to represent the external electric field, the length and the width of the material which is present here. So most of the time we are going to use a material which is called as silicon. So there is no need for us to represent this separately as silicon. Whenever in your question paper they are not representing anything, you can directly use the word which is called as silicon. Okay, so you can see there the current formula for integration will be given by I is equal to double integral J into dy into dz. So we have to solve this particular equation, integral equation, by using the limits y is equal to 0 with respect to w and z is equal to 0 with respect to t, and the resistance will be solved by using the integral equation, integral 0 to the maximum length of the silicon material which we are using into rho of x. Conductivity will be integrated with respect to x and divided by width of the particular material and time period of the particular material. So automatically we will be getting the final formula for resistance as L divided by sigma WT. Okay, sigma represents your conductivity rate, W represents the width of the material, and T represents the time period of transition. Okay, time period of recombination, not transition, time period of recombination. So in your gate point of view, this resistance will play a major role. They will give the material as silicon and they will give this diagram. Okay, so what they will tell you to find is, they will give the length, they will give the width, and also they will give the time period. And with respect to this, you have to calculate the resistivity rate. The resistivity rate in this case is given by the formula. Note down this formula: L divided by sigma W into T. Okay. Now let us move to the next part. 1 minute. So this is how the mobility is changing. Okay, first itself we are talking about mobility. Mu is equal to E divided by Wn or Wp. That's what we are talking. So see here how the mobility movement has been changed with respect to increasing doping concentration. See here, first the mobility value is very much higher. After some time period, if the doping concentration of both electrons and holes are increasing, then automatically it is dropping to 0 point of view. That's what I have said you in the carrier motion 3. What happens in the carrier motion 3? The acceleration as well as the deceleration moments are getting equal to 0. That's what is given here also. If the concentration of doping is higher, lower mobility will be obtained. If more defects are there, mobility will be small. That's why I have already told you, we have to overcome the defects that are present in this particular material. So tau is inversely proportional to mu. Sorry, tau is directly proportional to mu. So therefore, whenever tau is smaller, automatically mobility is also becoming smaller here. Okay, so this is how the mobility changes. And in the second case, if the electric field strength comes into the picture, automatically there will be separation between electrons and holes. And if the applied electric field is very much lower, then automatically the electrons and holes will go to the saturation state by combining with respect to each other. This is explained by using this graph. See here, at the initial stage, the gap between electrons and holes is very much higher because the value of mobility is constant. Okay, the value of mobility is constant. That's why the electrons and holes will be having a marginal gap with respect to each other. But suddenly, due to increase in the electric field, automatically both the electrons and holes will combine with each other, and at last it reaches the saturation state. So this is best explained by using the changes in mobility that is observed by using the second theorem. And in addition, we are also having the energy band, which we have discussed in the previous class. We have to take the center thing as energy band, and the upper and lower difference between the energy bands are also represented here. Okay, so you can see there, this is your total electron value Pe plus Ke. Okay, so this is your formula Pe plus Ke. The number of energy band in P combined with the number of energy band in N type, that represents your Pe plus Ek. Okay, so you can see that Ke is represented as for holes and Ke is represented for electrons, as well as Pe stands between Ke for both electrons as well as holes. And what you have to do is, you have to assume, always assume in this particular case, that the reference value of energy band for the applied electrons as well as holes, the reference value must be always equal to constant, which cannot be changed for every period of time. From this reference value only, we are going to determine whether the electrons and the holes are changing with respect to each other. If the electrons and holes are not changing with respect to each other, that is not a problem. But we know that the electrons and holes are changing with respect to each other. That's why E reference in this case will be given as constant. Okay. And the formula for finding P is very simple. You have to do the difference between EC minus the reference value, which we have given in this case as constant. Constant means maximum. We will be substituting 0 in our equation. So PE is equal to EC. Okay. So next case we will be having about 1 minute. So you can see there, in this case, we will be having the energy band representation for electric fields too. So these equations are very, very important. In the gate question, they will ask you about these equations. They will give you the value of differentiation with respect to the electric fields. What is the energy gap? What is the energy gap in N? What is the energy gap in P? They will give that and you have to solve for that particular equation. So you can see there, E vector is equal to 1 divided by Q into del vector into EC, and in this case Ex is equal to DEC divided by Q into dx, or else DEV divided by Q into dx, or DEI divided by Q into dx. This represents that the electric fields and the applied voltage are related with respect to each other. Okay. So next is the energy band diagram. This energy band diagram and this Fermi level we have already seen in the first class itself. We all know how to draw the Fermi level, and from the Fermi level how to calculate the energy band, that you know well. So now let us go to the Poisson equation. Okay, let us discuss about the Poisson equation in detail. Okay, so now I have given you the overview for the semiconductor. After that, we have discussed about the minority change diffusion carrier equation also we have seen. Now what we are going to do means we are going to discuss further about the semiconductor equations, because 5 independent equations are represented here with respect to P of R vector, N of R vector, V of R vector, Jp of N vector, and Jn of Jn vector. This J represents your current density. P and N regions are there, and the volume of R vector is also represented. That means volume of a particular area is represented. That's why they have given this diagram. Observe this diagram. There 4 different directions are present here. When externally applied current density is present, what happens to Gn, what happens to Rn, and finally what is the resultant output J of x plus dx will be represented here. So these are all the semiconductor equations. Just try to copy it. In the meantime, dou P divided by dou T is equal to minus del into Jp vector divided by Q plus Gp minus Rp, and dou N divided by dou T is equal to minus del into Jn vector divided by minus Q plus Gn minus Rn. Whereas in this case, both the derivative equations which are differentiated with respect to each other will be equal to 0. That's why you are getting del dot epsilon into E vector plus rho. Therefore, if you solve this, you are getting the value of a JP vector, JN vector, conductivity rate, E vector with respect to R vector in this case study. So these are all your semiconductor equations. Now let us go for the second case study where we are having the minority carrier diffusion equation. This equation we have seen in the previous class by assuming that the initial state conditions are in equilibrium. So therefore, we will substitute dou into del P divided by dou T is equal to 0. And in the gate question paper, they have given you the values of GL. For this GL, you have to solve this particular equation. Automatically, GL is equal to del P divided by dou P. By assuming the initial condition, we are going to take place. But here, the drift problem condition is entirely different. So you can see there, the drift problem condition which is given here is entirely different. JP vector is equal to P into mu P into del vector of FP divided by Q. Jn vector is equal to N into mu N into del vector of Fn divided by Q. Next, we are going to see what is the possible solution for obtaining the zero case and for obtaining the value of del n which is equal to 10 power 14. So you can see there, as usual I have told you, this part will be completely neglected. Therefore, you will be getting GL is equal. If you want to calculate del n is equal to GL into tau n. Okay, so the value of del n is equal to 10 power 14 at x is equal to 0. Now analytical solutions, let us obtain the analytical solutions with respect to the time periods for del n. If any changing x is there, automatically del n of x comma t will be calculated. So you can see this first graph. You can observe here, no initial conditions are present, x is equal to 0. That's why you are getting del n of 0 into e power minus t by tn, whereas if the value of x is equal to 1 with respect to the time period, then automatically del n of x comma t is equal to g into tau n into 1 minus e power minus t divided by tau n. Okay, so this is your equation for solving the analytical solution. So same steady state condition, and if no generation or recombination rate is present there, the same formula will be applied. Now let us go and see about what happens to one side carrier diffusion. So you can see there the length scale, how much the scale length will be there, within how much short duration the solution can be obtained, and what is the intermediate rate. If any intermediate rate is there, then what type of solution can be obtained, that is represented here. So you can see there the length will be long, where the diffusion length is always lesser than that of actual length. That is solved by using the solution which is called as a decaying exponential. Suppose if the original length is less than the diffusion length, then automatically a linear solution will be achieved. And in case if L is approximately equal to the diffusion length, hyperbolic functions will be used for solving. Why I am saying this is, in your gate question paper, they will give you this condition. Assume that the original length of the silicon material is greater than the diffusion length. In this case, what equation you should use? Because I have told you 5 different equations. Out of those 5 different equations, you have to choose one. That's why in this case, you are getting the decaying exponential only if length is greater than the decaying length of the recombination rate. Whereas if the original length is much lesser than the diffusion length, then automatically a linear scale solution will be obtained. You have to take the linear equation and you have to solve this particular problem. Then after that, intermediate rate L is approximately equal to LD. A hyperbolic function can be used for solving this rate equations. Okay, so if you want, you can note it down. Okay, just draw a table and you can note it down because conditions will be given here. Okay, conditions will be given here. Okay, so I think I will move to the next slide for further discussion about the next case studies. So we will discuss this. We will discuss in the question paper. I have solved the question paper separately. So let us discuss those questions later. Now let us come to a discussion where three unknown equations are present. Okay. Now three unknown equations are present. In this case, what you are going to do, we are going to solve this unknown equation by using a steady state equilibrium, which is represented by using a theorem which is called as Poisson equation theorem. Okay. So you can see through the last state 0 is equal to minus del dot epsilon into E vector plus rho. This represents your Poisson condition. In case if rho of x, E of x and V of x remains unknown, and if three equations are unknown, then automatically the Poisson equation will come into the picture. Okay. So Poisson equation is usually a counting process. Okay, repeat again. Poisson equation is usually a counting process. So I will tell you a simple example first. First, let us assume the observing number of occurrence of certain event. There are event is happening. We are going to observe the occurrence of certain event over a specified period of time. So what happens in this case means we can consider them as happening under a Poisson process, and for this three different conditions are defined. First condition is that disjoint time intervals must be independent. So you can note down this three conditions for Poisson equation. First one, disjoint time intervals are independent. The probability of single occurrence during a small time interval is directly proportional to the length of interval. That means P of t, probability of a time period, or the expected probability P of E is directly proportional to the length L, original length L. That is your second condition. Third condition is if the event has been occurring for more than once, then automatically the small time interval that is present for occurring a particular event will be completely neglected. I repeat the three conditions again. Understand it clearly. First condition is that the disjoint time intervals must be independent with each other. Okay, I repeat again, the disjoint time intervals must be independent with each other. After that, the probability of a single event occurrence during a small interval of time is directly proportional to the length of interval. You can simply write as P of E or P of T is directly proportional to length. Okay, and the last condition is if more than one event is occurring, then the probability of more than one event during a small time interval can be neglected, because we cannot always say that the entire event can occur by using the given time period. That's why always we are neglecting the small time interval that is present in this case study. So this is called as your Poisson equation. So now let us calculate the value of rho of x, n of x, p of x and e of x. Okay. So now this is your energy band which is used for solving the Poisson equation. Okay. So two different boundaries are given here. One is your left side EF boundary and the other one is your right side EF boundary. Between these two boundaries, we are going to calculate the Poisson equation, and you can see there the Poisson equation is beginning with the energy band EF, and after this it is processing to the current state density which is present here. Then after that we are going to do the electrostatic potential by just flipping the E band upside down. From this flipping we are going to calculate the E field from the slope. Then we are going to calculate n of x and p of x from the E-band diagram which is given. Finally, rho of x it will be calculated from the value of n of x and p of x, and the diffusion current will be solved from equation 5 and from 6 that I have told you previously. So automatically the equation will be represented as EC of x is equal to EC reference, the reference value for electric field will be given minus QV of x. Okay, so again this can be solved by using the equation epsilon of x is equal to 1 by q into dEc of x divided by dx. So this is how you have to calculate the Poisson equation if the given energy band is having two different boundaries. First we have to find what is the value of n of x, and we have to find what is the value of p of x. Then finally, after finding these two different values, we can automatically find what is the value of rho of x. So if you are finding the value of rho of x, that automatically indicates that the Poisson equation is completely solved. So this diagram represents the energy band between the condition x is equal to 0, the reference condition, as well as the electric field that is present in the y-axis. So you can see there the red color line which I have represented here, that is your intermediate energy that is applied. Below that we all know that EI will be present and EC will be present at the upper side of EF. So this red color line indicates that the Poisson equation is present with both upper as well as lower limits. Next, from the E-band diagram, what we are understanding. So we can define this E-band diagram with respect to the electrostatic potential versus the position, electric field versus position, electron and hole densities versus position, space charge density versus position. So four things you can observe by using this E-band diagram. Now the equilibrium condition has been given here. Since the equilibrium condition has been given here, two questions are raising in this particular case. What is the width of the depletion region? What is the maximum electric field that is present in this particular NP junction? We are going to represent it by using an equation which is called as VBI is equal to KB into T divided by Q into inland of ND into NA divided by NI square. So this is your depletion region. So you can see that the cut box here represents your depletion region, and N will be having the applied voltage level, and for P the voltage level is equal to 0, and for both N and P state the value of conductivity is equal to 0. Okay. So this is your Poisson. You can see I have typed it separately. I will also show you the equation separately. So you can see here this is your Poisson equation. Minus del square into V is equal to rho divided by epsilon. This is your Poisson equation. That's what they have given here. 0 is equal to minus del into epsilon s into E vector plus rho. Okay, so make a note of this Poisson equation. Remember this Poisson equation. Why we are having 0 in our left hand side? Please remember it. Okay. So now let us go to the problems. Some gate problems are there for solving. So we will see the gate problems here. Okay. So what we are going to do here means previous gate question papers I have solved, because we have to combine all the three topics that I have taught you. First, let us see through the comparison type, what happens to the doping concentration. Okay, so let us see about the 1 mark here. Okay, so you can see there, we can read the first question here. A p-type silicon sample has higher conductivity compared to n-type silicon. What they are telling here is rho value of p-type is greater than the rho value of n-type. So this is your first initial condition. Okay, having same dopant concentration. Dopant concentration How it will be represented? The dopant concentration will be represented by using the value of what? N is equal to P. So you can see there, N is equal to P. They have represented, since N is equal to P, Q is always same for both N as well as P type. That's why in this case study, we have defined the electron mobility of mu n. We all know for silicon, I have already told you, if they have not given any material, if they have not given silicon or germanium, you should always take the value of silicon and you should solve it. That's why in this case, they have taken the silicon directly and they are solving it. So you can see there, the value of silicon, the mobility rate of silicon is 1350 centimeter square at room temperature, and for P type it is 480 centimeter square at room temperature. So therefore, electron conductivity sigma n is equal to n into q into mu n. Hole conductivity is equal to sigma p is equal to p into q into mu p. Okay. So in this case, sigma n is greater than sigma p. It is false. Okay. Sigma n is not greater than sigma p originally. Okay. So that's why a false condition has been raised here. Okay. Now let us go to the second question. The probability that an electron in a metal occupies the Fermi level at any temperature greater than 0 Kelvin. So they have given 4 options for you. They have given 0, 1, 0.5 and again 1.0. So now let us calculate this. So you can see there, they have given the explanation also. Suppose if the probability of an electron that occupies at a time period t greater than 0, then automatically what happens in this case? That's what I have told you. The conduction and valence band will be overlapping with respect to each other in case of metals. Whereas in insulator only, the probability of occupying the electron in the Fermi level is 0.5. So the option is C. It is 0.5. Here they have given the value of electrons that occupies the Fermi level at 0 Kelvin. So it is equal to 0.5. Third question, the drift velocity of electrons in silicon. Okay, what is the drift velocity of electrons in silicon? We all know the formula. Vd is directly proportional to E. The same thing they have given here. Yeah, the same thing they have given here. Vd is directly proportional to EE. So therefore, the drift velocity is given by the formula mu n is equal to q into tau c divided by mn, and this tau c represents your average time between the collision. This is represented by using the energy band diagram, which is given here. In the x-axis, you are having the applied electric field, and the drift velocity for silicon is present in the y-axis. This is how the collision time period is increasing. So therefore, you will be having the answer as increasing linearly with electric field and gradually saturates at higher values of electric field. So you can see there, at higher values of electric field, what is happening here? Saturation is occurring. A constant convergence point is represented here. That's why they have given us linearly. When the applied electric field is smaller, then automatically you can see linear increase. Then after that, saturation point will be achieved. The convergence will be same. So therefore, in this point, you will be having the saturation of electric field at higher point of view. Okay. So next, in a p-type silicon sample, the hole concentration is 2.2. So they have given the concentration of holes directly. Okay, they have given the value of p. They have given the value of Ni also. So directly, what you are going to do means what they are asking here in a p-type hole concentration, intrinsic carrier concentration they have given. The electron concentration they are asking. Okay. How you are calculating the electron concentration? By using the formula, very simple formula, Ni square divided by P. P also they have given, Ni also they have given. You have to put the square here and you can directly get this answer. Okay, so 2.25 will be getting as 1. So 10 power 20 divided by 15 power 15 will give you 10 power 5. Okay, 10 power 5 centimeter cube. So this is a direct question. Okay, so this is very direct question. Very easy formula, Ni square divided by P. Okay. So fifth question, a small concentration of minority carriers is injected into a homogeneous semiconductor crystal at one point. Okay, I repeat again, only a small concentration of minority carriers, not majority carriers. So minority carriers will be injected in a semiconductor crystal at one point. An electric field, okay, E they have given 10 volts per centimeter is applied across the crystal, and this moves across the minority carriers of a distance of 1 centimeter. Okay, time period also they have given, and distance also they have given. They are telling you to calculate the mobility. Okay, they are telling you to calculate the mobility. We know that mu is equal to Vd divided by E. Okay, so we want to calculate first. What we should calculate means we should calculate this drift velocity. They have not given the drift velocity here. They have given the value of E, they have given directly. Okay, 10 they have given, but what you need to find? You need to find Vd. We all know that we can calculate the drift velocity by using the distance and time. So V is equal to D divided by T. The same formula they have applied here. Distance they have given, time they have given. What is the distance? 1 centimeter, time is 20 into 10 power minus 6. If I can convert it into seconds, then automatically you are getting this as 50,000 centimeter per second. Here you are going to apply this Vd and you are going to get the value of mobility. Okay, so it is somewhat indirect because you are going to find the value of Vd with the help of distance and the time period which is given here. Okay, so the next thing, they are just asking the unit of Q by Kt. Okay, what is the unit of Q by Kt? We all know what is the unit of Q by Kt. Yes, anyone? What is the unit of Q by Kt? You have to combine two different units here. First, you should know about what is the unit of K. See, this is very important question. Okay, because I think I have not told you about this one. Only I have told you about the formula and how to apply it. See, in many of the cases, they will ask you about this unit representation. Okay, in an indirect manner, they will combine two different formulas and they will ask you the units from this. So, what is the value of K here? What is the value? What is the unit of K? Boltzmann constant is represented by using J divided by K, and the unit of Q is Coulomb. So automatically you cannot get this J or J by K. Okay, so automatically A or B is going to be right. So you can substitute directly here C divided by J divided by K into K. So automatically A and K will be getting cancelled. C divided by J will be coming here. So automatically 1 divided by J by C. J by C, the unit of J by C is V volts. So V power minus 1. So V power minus 1 is the unit of Q divided by K into T. I repeat again, this is very important. See here, first you should know about what is the unit of the Boltzmann constant. The Boltzmann constant unit is J divided by K, and the unit of Q is Coulomb. So C divided by K into J divided by K. K and K will be getting cancelled. You will be getting Q divided by J. Q divided by J, the value of the unit of Q divided by J is volts. So therefore 1 divided by V, we are getting the inverse as V power minus 1. So this is the unit of Q divided by K into T. Okay, next. Room temperature they have given. So let us read the question completely. The intrinsic carrier concentration of silicon sample at room temperature 300 degree Kelvin is 1.5 into 10 power 6. So they have given you the value of Ni if after doping. Okay, doping is occurring here. The number of majority carriers, not minority. Okay, they are asking you about the minority carrier density. Okay, they are asking you about the minority carrier density. They have given you two different values. One is Ni and the other one is after doping the majority carrier. That means N value they have given. Yes, they have given here. So you can see here. Ni 1.5 into 10 power 16 per meter cube. N is equal to 5 into 10 power 20 per meter cube. So what is the formula here? Same formula. There we have used P. In the third question we have used P, but here you are going to use the formula as P is equal to Ni square divided by N. Direct substitution. So option is 4.5 into 10 power 11. 1.5 into 10 power 16 the whole square divided by 5 into 10 power 20. Automatically you will be getting 4.50 into 10 power 11. Okay. So what now tell me about the eighth question. We have seen the table in the first class itself. Okay. So tell me what is the band gap of silicon at room temperature 300 Kelvin? It is 0.80 electron volt. It is a direct question. Okay. No need to find anything. At room temperature, the band gap of silicon EB is equal to 0.80 electron volts. Okay. So now ninth question. N-type silicon is obtained by doping silicon with N-type silicon is obtained by doping silicon with what? Germanium or boron or aluminum or phosphorus? Neon? Automatically N-type silicon, if it is doped with phosphorus, you will be getting the doping condition of silicon. That's what they have given here. So what they have given here, for N-type doped silicon, pentavalent impurities are added. Okay, so impurities are present, so you have to remove that particular impurities. That's what we have discussed. By using this phosphorus, you can directly remove it. Okay, the impurity commonly used for realizing the base region of a silicon in NPN. So how will you realize any impurities are present in NPN case? So you can use indium as one material for realizing the impurities that are present in NPN transistors. Okay. So we will look after the problem. These things and all you can study. I will tell you about the problem here. Okay. Now let us see through this 12th question. A silicon PN junction at temperature, room temperature, they have given 20 degrees centigrade as a reverse saturation. Oh, yeah. Now see here. Now what I have taught you in today's class, the reverse saturation condition. Now they have given us the reverse saturation current as 10 PA. The reverse saturation current at the room temperature. Okay, now they are asking, they have given for 20 degrees centigrade. Okay, they have given the reverse saturation current for 20 degrees centigrade. You have to solve the reverse saturation current for 40 degrees centigrade. Okay, so we all know that at 20 degrees centigrade, the reverse saturation current is 10 PA. We have to calculate for 30 degrees centigrade. Then only we should go for 40 degrees centigrade. Okay. For 30 degrees centigrade, automatically 10 degree rise in temperature will be there. So you are getting 20 PA. But for 40 degrees centigrade, 20 rise will be there. See, I think you can able to understand it. 20 degrees centigrade, they have given 10. For 30 degrees centigrade, 10 plus 10, 20. Again, it is going to rise as double time, 20 plus 20. What happens to the 50 degrees centigrade? 40 plus 20. Sorry, 40 plus 40, 80. Okay, 80 PA. Now they have asked you only for 40 degrees centigrade. So you are going to get the values as 40 PA. Okay. Next, the band gap for silicon at room temperature. We all know that 1.1 electron volts. So, yes. Oh, let us see 1 minute. Yes, let us see through this problem. The electron and hole concentration in an intrinsic semiconductor are Ni per centimeter cube. Okay, Ni per centimeter cube at 300 degree Kelvin. Now, if acceptor impurities are concentration of Na per centimeter cube at 300 degree Kelvin with B. Okay, so in the presence of impurities, what will be the value of Na per centimeter cube? That's what they are asking. It is also a direct substitution. Na square divided by Na. So automatically electron concentration will be present. So Na square divided by Na is the direct formula. which is applied here. Okay. Next. Which of the following is true? A silicon wafer heavily doped with boron is a P plus substrate. A silicon wafer lightly doped with boron is a P plus substrate. A silicon wafer heavily doped with arsenic is a P plus substrate. A silicon wafer lightly doped with arsenic is a P plus substrate. So you have to look at this question clearly because they are confusing here. Heavily doped condition and lightly doped condition with arsenic and boron is represented here. Silicon, when it is doped with boron, heavily doped or lightly doped. So we are using only silicon with boron only. Okay, we have not expressed any case that the silicon is going to be doped with arsenic. Okay, so either in A and B, one option will be correct. So silicon heavily doped. Okay, we cannot dope lightly for P plus substrate. So I think A is correct here. Yes, A is correct here. Silicon wafer, when it is doped in heavy concentration with boron, P plus substrate will be obtained here. Okay. Next, in an N-type silicon crystal at room temperature 300 degree Kelvin, which of the following can have a concentration of 4 into 10 power 19 centimeter cube? Where we have seen this 4 into 10 power 19 centimeter cube. We have already seen the concentration of holes is present here. Okay, the holes will be having 2.05 into 10 power 15 centimeter cube, whereas if you go for the doping concentration, automatically you will be getting the value as 4 into 10 power 19 centimeter cube. Okay, next. Drift current in semiconductor depends upon what it is depends upon. The drift conductor in semiconductor, what it is depends upon. It depends upon both the carrier concentration as well as the applied electric field. Okay. So now let us see this question. 20th question. A silicon bar is doped with donor impurities. Nd they have given the intrinsic carrier room temperature they have given. Ni also they have given. So what formula you will apply here? Same formula. Ni square divided by N naught, automatically you will get as a 10 power 5. Okay. So this is a direct question. I think some questions are solved indirectly. So you can see here. I have already told you. They have given you. They will give you the figure. From the figure, they will ask you some different types of expression. So you can see there in the figure, ln of Pi is plotted as a function of T, where Pi is the intrinsic resistivity of silicon, T is the temperature, and the plot is linear. Okay, we all know that our plot is linear here. So automatically, what we are getting here is so you can see there what is the slope. Anyone is having any question? I think some disturbance is there. Okay, so if any doubt is there, you can ask me. That is not a problem. Okay, so yes, 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 yes. Yes, so 1 minute, 1 minute. Just a minute.